So here is our unit on vectors. And I think we've kind of been through this thing before. When we talk about a vector, and I say, what is a vector, or what does it have? What are the two words that are going to come out of your mouth? Oh, okay, hold on. Okay, give me one, Anthony.
Magnitude.
Magnitude, all right, and Ishan, the other one? Direction. So the thing about vectors are magnitude and direction. Now, you can play with vectors mathematically, but before people really did the mathematical stuff, they played with vectors graphically. And in order to play with this graphically, you have to establish, a symbol or a shape that could tell you a magnitude and a direction. And the classic shape is an arrow. Now, there is one thing about the vector, the arrow vector, that I draw that goes to this idea that when you do vectors graphically, you have to make them just the right length in order for things to work out properly. So if this arrow was going to point off in this direction, most people will come out here and they'll start to put an arrow tip on the end. I actually put my arrow tip kind of recessed from the end, because if this is the exact end of my vector, I don't want me drawing a sloppy arrow tip and ending up adding length or confusing where is the exact end of this thing. So when I draw my arrows, at least when I'm doing this graphically, you will see me most of the time recess my arrow indicator from the tip. And going into terminology, this end of your vector is referred to as the tip, and the other end, where it originates from, is referred to as the tail. Now, one thing about vectors graphically, when you're drawing them on a piece of paper, I know I'm going off screen, but that's all right. You can draw vectors anywhere. You can move a vector around anywhere you want on a piece of paper. Even if you have this original place where you draw it, you can move it anywhere you want onto your surface, as long as you don't alter two things. One, how long it is, and two, what direction it points. So if I needed, for example, to move this vector somewhere else onto my piece of paper, one of the things that I would have to establish is, this is about 51 centimeters. So anywhere I want to move this, I would need to be sure that I maintain it being 51 centimeters. And the second thing is, I would have to make sure that wherever I wanted to move it, I would need to keep it, and I'm eyeballing this. If anybody's ever seen a real drafting table, they got all these cool little tools that will make sure that once you establish the direction that your straight edge is at, that you can move it around and it won't get wiggly on you. It'll just stay perfectly, wherever you want to move it, it'll always stay parallel to the original direction. So I'm kind of eyeballing this one here. I think that looks acceptably straight. So if I came back and moved this right there, yeah, it's not the greatest. I can see I'm a little bit wider here than I am there. We have to pretend that I did this perfectly. As long as this perfectly points in the same direction that this originally did, and it's the same length, it's the same vector. So these would be considered the same thing. So you can move, in a sense, you can move vectors around in space as long as you don't alter length and the angle. Now, getting back to this idea that we're going to use arrows to represent our vectors, the length is the thing that represents the concept of magnitude, and I'm going to call it the orientation in terms of where it points. That indicates the concept of direction. Now, the one thing about vectors that opens up a whole new world for us is the idea that now we can talk about at least two-dimensional stuff. Up until this point in time, when we talked about direction, you really only had two options: this way or that way, or this way or that way. And when someone, what if it went here? We basically said, you're not allowed, which is not very realistic, because, and this is kind of a, I know what the right answer is, but my answer would be slightly different. When we talk about dimensions and like what kind of a world do we live in, how many dimensions will people usually bring out? They'll bring out 3. I would argue a little bit on that one and say, I think we primarily live in a 2-dimensional world, because basically what we do is we move around on the ground. And occasionally we have this up and down dimension that we access, but for the most part, especially when we talk about motion, we are usually just moving around on the surface of the Earth. So in that regard, I think 2 dimensions is what really dominates most of the motion that we go through. And one of the cool things is, if you learn how to deal with vectors in 2 dimensions, going into a 3rd dimension, the concepts, how you do that, are similar to how you play with them in 2 dimensions. So going from 1 dimension to 2 dimension is like, holy crap, that was like a big step forward. But going from 2 dimensions to 3 dimensions, if you get the 2-dimension stuff, many people end up realizing, that's not so bad. I just got to add a little tweak that's very similar to what I was already doing with the 2-dimensional stuff to bring in that 3rd dimension. We will not go 3D, okay? We will stick to 2-dimensional stuff, but sometimes our 2-dimensional stuff will be like surface of the Earth 2-dimension. Sometimes our 2-dimension stuff will be vertical 2-dimension, which means we can go anywhere in this plane, but we wouldn't be moving like side to side while whatever's going on is happening. Yeah, Anthony.
Are we going to be like summing the vectors?
Absolutely. Yeah, this is just the beginning. Okay, so now we have to come up with our concept of a frame of reference. And this is where we connect back to cool, well, I call it cool math stuff. Because doing vectors is actually pretty easy, but we don't use, when people talk to me about directions, you can go in any direction you want. We can come to this frame of reference, but if I were to ask most of you, all right, what do we do with this? You would give me this thing where you'd say, oh, that's a Cartesian coordinate system. We do X and Y. And it's not that we're not going to do this, but that's not the primary way that we look at vectors. The primary way we look at vectors is something that looks exactly the same way. Anybody know what the system is that we're going to use?
Like a four-constant basis vector, like I and J.
No, that's this still. And I got to tell you, I will be picky about the I and J stuff. I'm not. I remember the first time that I ever got exposed to that, and I asked somebody, well, what's I? Well, it's the horizontal unit vector. Well, what the hell is that? Well, it's this thing that goes like that, and it's 1 unit in length. And I'm like, well, what the hell good is that going to do for me? Well, it's I. It's like, so if I need 7 units that go horizontally, I call it 7I. Why don't I just call it 7? No, well, it needs to be I. I'm like, that's stupid. I don't understand why you need we will have different terminology that we use to highlight that it's the horizontal thing, but in the pure math world, they do use the I and J thing. So for those who have had exposure to that, I am hoping that some people are going, damn, I learned just about all of this stuff in my math class, and it's like, you did. All we're going to do here is apply it, you know, in the physics world. So I'm going to try and be patient with you I and J people, but I know you're out there. I don't do it that way. Well, I don't use that kind of notation, but I know it's there. This approach I don't know if you've heard the terminology before. This approach is a rectangular approach, because when you say, where is that point, you're only allowed to do 2 things on this frame of reference. You are allowed to move horizontally or vertically, but you are not allowed to go anywhere in between. So when someone says, how the hell do I get there? You go over to here, and then you go up to here, and you call this the x coordinate, and you call this the y coordinate, and then when someone says, well, how do you locate that place in space? You have a point, and you have a set of coordinates, okay? But the idea with rectangular coordinates, if someone said, wouldn't it be quicker just to like shoot right there? It's like, you're not allowed to do that. You can only move horizontally or vertically in terms of taking individual steps. Now, to approach this in a different fashion, there is a different coordinate system where you can still map out every single place in space, but you get there differently. Anybody know what it is yet? Come on. Use the polar coordinate system. Because if I say you're doing polar coordinates, get to that point, where do you start?
At the origin.
You start at the origin, and then where do you head?
Well, you shift the angle.
You orient yourself
Yeah.
to the direction you want to go, and then what do?
You just go.
You go straight there. So in the polar coordinate system, that's what you would do. And the thing that you need to know is this, which is an angle, and it's theta. And then what's the other thing that you have to know? You need to know how far away is the spot so that you don't overshoot it or undershoot it. Anybody know technically what letter they use for that one? Oh, this is good math review. It's R. So in the polar coordinate system, we still call that same spot P, and it still gets an ordered pair. But the ordered pair is different from this one. It's how far out do you go from the origin, and what angle do you go at? Okay? Now, we have to, there's some additional things that, you know, pure math people would say, oh, you should remember all this. One of the things to help you over here is this direction is positive, this is negative, and this is positive, and this is negative. So when people say plus or minus, you know which way, horizontally or vertical, to move. What's the equivalent here?
Is it r cosine theta and r sine theta?
No, we'll get there. That's where I'm kind of throwing this out at you like these are 2 different things. There's actually mathematical connections between the 2, and that's where you're already there. So Hopefully you don't get bored with what I'm going to have you do initially, because it'll be much more basic.
If r is negative and the vector points in the opposite direction.
Right. Now, I will tell you from our vector treatment, we will never have a negative vector, so we won't need to worry about that. The thing that I'm getting at is, how do you know where your angle is? Because I didn't label it.
What quadrant the theta for?
We have this quadrant thing. 1, 2, 3, and 4. And what about a degree measurement here? What's kind of our, because remember there's a, what was it, our frame of reference, and then we have the reference point. Now the reference point for our R is the origin, because we always start from there and move out from that. Where's our reference point for our direction?
It's not really a point, but it's the pole, which is the positive side of what would be.
Right. What we call the positive x direction here becomes how many degrees?
0.
0. And then which way do we increase from here? We go counterclockwise, so this becomes 90, this becomes 180, and this becomes 270. Okay? Now, for people who have had some exposure to this, because I kind of think you have, even if most people go, I don't remember any of that stuff. Well, you'll relearn a little bit of it when we play with this. There is one thing that I'm going to be picky. At higher levels, people will be okay with you doing this, but I like to keep things like very mechanical. So when it comes to moving through the quadrants, if you remember, I mean, technically moving in a positive degree measurement, you always go counterclockwise. But when you get to this fourth quadrant, and there's the idea, well, can't I just go like this way with a negative number of degrees? I will not allow that. Okay, in here I will always emphasize I want your final answers when it comes to direction things from 0 to 360 degrees, and we'll address that when we do the mathematical side of things. At higher levels, I am sure that they'll say, hey, you can use negative number of degrees. There's a reason that I'm going to be picky about it, and it has to do with your calculator. And so we'll address that when we do the mathematical vectors.
Are we going to not use radians?
No, we won't. We will stick in degrees. Eventually there'll be some things that do radians, but I think from a conceptual perspective, when it comes to this, I have more often seen degree measurements because that's what's used in everyday usage. Because I think if you ever told a pilot, dude, head towards 45, or 3.2 radians, they'll go like, what? And when you tell them in degrees, they're like, oh yeah, I get it. So I think on a daily basis, people usually play with degrees more. But again, you could do this exact same thing and just have it entirely be radians, but we'll stick to degrees here. Okay, so this is kind of your backdrop for vectors. And I mentioned earlier that there are two ways that you can play with them, graphically and mathematically. And the graphical thing is make it the right length and point it in the right direction. And just be very careful, because the idea of being correct graphically means you physically made it the right length and pointed it at the right direction. When it comes to math, your correctness usually, when you're doing computations, it goes to, did you put the work together right, and then you actually do computations on a calculator. When it comes to graphical stuff, it is all on you. And it's as simple as point it the right direction and make it the right length. So what I'm going to do, we are going to do a very strict graphic/mathematical treatment of vectors like you would get it in a math class. And then what we're going to do when we're done with that is we'll connect with physics principles where we make use of vector concepts. So the first thing I'm going to have you doing is we are going to create a list of vectors. So I'm going to erase all this stuff, and I am going to put the list of vectors here. And these are the vectors we're going to play with when I'm going to have you work with them in our mathematical unit here on vectors. So you're going to want to get this recorded because this is the only time you're going to see it. So let's see. Yeah, I'm giving you the full 11 vectors. All right. Now, let me go back to my original picture. When we said, okay, I got a vector, it's a certain length, and then it points at a certain direction. The way you are going, there are different ways that you can show vectors in terms of symbols. In textbooks, for example, one of the things that they tend to do, and I think this is a regular thing that I've seen, unless there's a reason not to do this, they will use capital letters only for vectors. And then secondly, they will do one of two things. They'll either make it bold type, or they will put a little arrow over the top of the letter to indicate that, to kind of highlight, this is a vector. You know, so when you say, the answer is 4.3, and if that's all you give, you haven't given a complete answer. Because if it's a vector, you will have to say, it's 4.3 what, but then you will also have to follow it with what number of degrees does it point at. So when I go to write these, because I can't do the bold type thing, if I'm going to talk about this vector, I will use a capital letter, and then I'll have an arrow over the top of it, and then I will express it as an ordered pair. And the first thing is, at least as a variable, it would be just the capital letter without the arrow, and this means what is the magnitude of the vector. And then the second thing would be the angle that it points at. So what I'm going to do is I'm going to put a list of 11 vectors up here. And you need to get those copied down, because the next thing I am going to do is I'm going to give you a piece of graph paper, and I'm going to have you draw all 11 of those vectors, okay? And I'll give you instructions about how to do that. Once we get it going, it's like, oh, this is simple, but just to kind of preemptively scare the crap out of you, maybe, when it comes time to grade this, I have made an overlay, and I'm considering my stuff as the perfect stuff. I have done exactly what you're going to do, and I have made an overlay, copy on a transparent piece of paper. I'm going to lay this thing on top of yours, and if yours doesn't match mine exactly, you're getting dinged. So you gotta take it seriously enough to be sure that you use the protractor and the ruler the right way. Okay? Yeah, Gabe.
Are all vectors start at the origin?
Technically, when you draw them as generic vectors, the answer to that would be yes. But once you actually start to get multiple vectors and you're like wanting to combine them somehow, then that would be no. And we'll deal with that later. That's kind of like the next step. Okay? So, hopefully you're comfortable with this, because I'm going to erase this now, and we're going to put the list of 11 vectors here. All right. Now, when it comes to what things can be represented by vectors in physics, we got all kinds of stuff. We got displacements, velocities, acceleration, forces, and we haven't talked yet about momentum. There are all kinds of things that could be vectors. The easiest way to deal with these, at least from a mathematical perspective, is just pretend that we are dealing with lengths only. Later, we'll have you playing with vectors that will look just like you're doing here, but they actually won't be just lengths. They'll actually represent things like meters per second, or meters per second squared, or newtons. So the first one, A, got B. C. D. One more here, and then we'll do another column. We got F. Okay, so this is what I refer to as your master list. Whenever I'm going to give you a task to do with these vectors, this is where you'll go to find the values for those vectors. So I'll give you a minute here to get that copied down, and while you're doing that, let's see how much time we got. Oh, yeah, we can. It's supposed to be over here. What are we, 15 minutes? Yeah. Oh, 20 seconds. All right. This is your piece of paper that will never leave this classroom. And I know it's not the fanciest. How are you gonna have your list with nothing out?
I'm writing on my computer.
All right. Now, in a moment, your first task here is going to be pretty simple. Dude, you have a protractor. Anybody else have protractors with them?
Yeah, I don't have one on me.
You don't carry it with you everywhere? Oh my God.
When did you ever use it? I feel like for some reason there were times that I did have to use it, but it's like, why was I so prepared?
Oh, okay, you don't want to.
Yeah,
Understood.
I brought one last year and like it shattered in my backpack.
Oh, that would be devastating.
Yeah, I feel like I was like required to get like a protractor. Nowadays I have like
I used to have
Okay. Now, here is what you have to do. Okay? I got better ones for you than that. Do you think I'm going to have you use wooden crap?
I heard wood is better.
We need rulers and protractors. And I do not normally leave these out because these are the good ones. Okay? So, if I see anybody like banging around with them, I will get pissed. I will tell you on the protractors, you're not going to need the protractors today because we don't have I don't think we have enough time to really get started on that. some of them have some rough edges because people have not been very nice with them. But these are the better of the ones that I have, and I saved them for this particular unit. The rulers in here, it's kind of a mismatch. I'm gonna say some of these plastic ones, not necessarily the best. The ones that are kind of transparent, these are the ones that are a little bit nicer. Again, you can always run your finger along the edge to make sure that it's kind of smooth. If there's one that's got a roughness to it, let me know and I'll move it into the crap collection. So here is the what you're going to do. Has everybody gotten this copy down? What?
Sorry. No.
Where have you been? Okay. Here is what you're going to have to do, because I know this is my edge on where I'm still, well, at least my hands are still on camera. This is what you're going to have to do with a ruler. You got your piece of graph paper here. What I want you to do on the first side here is more or less find about where the middle is, and I want you to go ahead and establish, I'll do this in a different color, I want you to establish your coordinate system. So I'm going to want you to run a line, your vertical and horizontal line, but remember we are doing polar coordinates, so I want you to label off on the edges here 0 degrees, 90 degrees, 180 degrees, and 270 degrees. And I want you to keep those notations kind of off to the edges, because you're going to be doing all your drawing in here, and that way this stuff would just get in the way when I go to correct things, and it makes it harder for me to see like where your stuff is. Yes? What do you mean? Yes, these need to be like perfectly straight. So you will need to come get a ruler to do this. Now hold on a second before I turn you loose so I can, because after I say go for it, I'm turning the camera off. Okay, so all you have to do today is draw these coordinate axes, get them labeled here. Be sure and I'm going to be very micromanaging here. Get your name up here, and one final thing about doing all of this. Pencil only. Okay, I do not want any pen, because if you screw up with a pen, I'm going to make you start from scratch. Okay, because when this thing gets turned in, it needs to be very clean. So you guys can get your coordinate axes set up. The rulers are up here, and then you'll hand it in before you leave, and tomorrow we'll get into the drawing.